All of this brings us up to the fundamental theorem of calculus. And the fundamental theorem of calculus is for definite integrals. And it says if we want to find the area under the curve, and remember that means between the curve and the x-axis, then we're going to integrate this function. Okay, and we're going to get that antiderivative. And then to find that area, since we're looking for a number, we're going to find that antiderivative evaluated at b. That's that top limit of integration, minus the antiderivative evaluated at a. That's that bottom limit of integration. So let's do one so you can see what's going on. So if we were to integrate this is going to use that power rule. So we're going to add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent. And we want to evaluate it from 1 to 2. So I like to clean this up before I start. So if I clean that up, I'm going to have 2x cubed minus 3/2 x squared. And we are evaluating from 1 to 2. So what we're going to do is we're going to plug the 2 in first, and then we're going to subtract, and then we're going to plug the 1 in. So when I substitute the 2 in, I'm going to have that. Subtract. And then I'm going to substitute that 1 in. So now we want to simplify all this. So 2 times 2 cubed is 16. And then if we simplify minus 3/2 times 2 squared, that's going to be a 6. If we simplify this, we're going to have 2 minus 3/2. So this ends up being 10 minus 1/2. Which is 9.5, 9.5. Now, one thing I want you to notice we didn't include the plus c here. And that's because it's really not going to be necessary. And let me show you why. So why don't we need the plus c? It's going to actually end up canceling out when we start plugging things in. So if we were to include the plus c here, look at what would happen. So I'm writing that in red over this so you can see. If we included the plus c here, then when we simplified, we would have had the plus c here. So then down here, when we plug the 2 in, we would have had the 2 cubed here, the 2 squared here, and then a plus c. And then when we substituted the 1 in, we would have had the 2 times 1 cubed minus 3/2 times 1 squared plus c. So this still would have simplified to 16 minus 6, and then we would have had a plus c here, and then we would have had a plus c here. So then we would have ended up with 10 plus c minus 1/2 plus c. So you could see if we distribute that negative, those c's are going to end up canceling. And that's going to happen every single time. So that's why we really don't need that plus c on these. Because when we distribute, it's always minus f of a, going back to the fundamental theorem of calculus. And when you distribute, you're always going to end up canceling those c's every single time. So that's why we're not going to include them. So let's look at another one. I'm going to take the next problem and write it on the next page. So with this one, to integrate, we're going to have to simplify. We can write that square root as t to the 1/2 power. Remember, there is no product rule or quotient rule for integration. So we have, if we distribute 6t to the 1/2 minus t to the 3/2 times dt. So we're going to integrate each piece separately. This is going to be the power rule. We're going to add 1 to the exponent, and then we're going to divide by that new exponent. Same thing here. Add 1 to the exponent, divide by the new exponent. And we're evaluating from 0 to 2. Now we need to simplify this. When you divide, you do keep, change, flip. So that dividing by 3/2 is the same thing as multiplying by 2/3. Same thing here. This is a -1. Dividing by 5/2 is the same thing as multiplying by 2/5. And we're evaluating from 0 to 2. And I'm going to reduce before I try typing numbers in. So this is 12 over 3, which is 4. And we are going from 0 to 2. So now we can plug numbers in. We're going to plug that 2 in first. It's always that top limit that goes in first. And we're going to subtract, and then we're going to put that bottom limit in. And plugging in 0 is going to be nice because this whole thing is going to be 0 that we're writing now. So this guy is 0. I'm going to go ahead and mark through it lightly. So we have to simplify this. So this is 4 times, this ends up being the square root of 2 cubed minus 2/5, and this is going to be the square root of 2 to the 5th. And remember, this guy's 0, so there's really a minus 0 there. So 2 cubed is 8. 2 to the 5th is 32. So we need to break those down. 8's the same thing as 4 times 2. 32 is the same thing as 16 times 2. And we would want to do that because we know the square root of 4 is a 2, so we could pull a 2 out. And that leaves a 2 under the radical. Same thing here. We could pull that square root of 16 out, which is 4. And that will leave a 2 under the radical. So now we have 8 square root of 2 minus 8 over 5 square root of 2. So both of these have a square root of 2. We can combine these by getting that common denominator. 8's the same thing as 40 over 5. So then 40 over 5 minus 8 over 5 means we have 32 over 5 times square root of 2. So there's our final answer. So I want to show you a few more examples. Let's look at this one. This is number 24. We could rewrite this as a 1/2 times x minus x squared over the cube root of x. And algebraically, that would be equivalent. And the benefit of doing that is pulling that 1/2 out. and then we can just deal with it later. Now, a cube root of x can be rewritten as x to the 1/3. So then what we're going to want to do is simplify what's going on. Remember, there is no quotient rule for integration, so we need to simplify before we start. So this becomes an x to the 2/3. Remember, when you divide and you have the same base, you subtract exponents. And then here, this is going to be an x to the 5/3. So then, when we integrate, we're going to add 1 to the exponent, and then divide by the new exponent. Same thing here. Add 1 to the exponent, divide by the new exponent. So this can be rewritten as 3/5 x to the 5/3 and 8/3 x to the 3/8 x to the 8/3. And now we can substitute in those limits. So I'm going to use a double bracket here because our final answer needs to be multiplied by that 1/2. Okay, so that's what happens when we sub in that top, that -1, subtract, and then we're going to sub in that bottom. So let's start simplifying. If we take -1 to the 5/2 power, we're going to get a -1. If we take -1 to the 8/3 power, we're going to get a +1. If we take -8/3 to the 5/3 power, -8 to the 5/3 power, we're going to get a -32. And if we take -8 to the 8/3 power, we're going to get a +256. So let's do some distributing here. We're going to have a -3/5 minus 3/8 minus, and then when we distribute here, that's going to be a -96/5 minus 768/8. So we're going to have -3/5 minus 3/8 plus 96/5. We're now distributing that negative, plus 768/8. So I'm going to cheat and type all that in my calculator. So I got 1/2 times. This ended up being 4569/40. So then our final answer is 4569 over 80. And if we wanted the decimal, this is a nice decimal. It stops. 0.1125 would be our answer. Let's do another one. Let's look at number 31. We're integrating from 0 to pi over 4. And it's 1 minus sine squared of theta over cosine squared theta. D theta. So we're doing a trig one. Okay, it's going to work the same way. There's not a quotient rule, so we need to rewrite this. So if we were to rewrite this one, we can split that numerator. So this is 1 over cosine squared theta minus sine squared over cosine squared. So 1 over cosine squared is secant squared. Sine squared over cosine squared is tangent squared. So we need to analyze this. We can integrate secant squared. The derivative of the tangent is secant squared. So if we integrate secant squared, we would get tangent. But we don't quite have anything for this. So let's think about those Pythagorean identities. We know that sine squared plus cosine squared is equal to 1. So if we were to divide everything by cosine squared, we can get one of those other trig identities. This is something you probably saw back in 172. This is tangent squared plus 1 is equal to secant squared. So we could reorder this. What if we were to move that tangent to the other side? Then 1 is equal to secant squared of theta minus tangent squared of theta. Okay, which is the exact same thing we have. So this guy is actually equivalent to 1. So we can rewrite this, and using that Pythagorean identity, write it as 1d theta, which is going to make this a lot easier for us to integrate. Okay, keep in mind this is also on your trig sheet. I just like going through the derivation process. I think it's fun. So then this integrates to theta, going from 0 to pi over 4. So if we do our substitution, we're going to have pi over 4 minus 0. So our final answer is going to be pi over 4.